Okay, so picking up part 2 of Unit 3-1 notes here, we'll pick up with this quick check here. So hopefully you have this on your example page, right? But anyway, this is kind of an example of inertial mass. So two rubber bands stretched to the standard length cause an object to accelerate 2 meters per second squared. Suppose an object with twice the mass is pulled by 4 rubber bands and is stretched to a standard length. The acceleration of that second object is what? Well, really, again, the way that I'm approaching this is just using force equals mass times acceleration. I know if I initially have 2 rubber bands and a mass and it's causing 2 meters per second squared, and then I all of a sudden make it 4 rubber bands, well, that's just going to double the force. So now I've doubled the force, but then they also say that the second object has twice the mass, so then what has to happen to the acceleration? Well, right, the answer on this one is nothing, because I've already doubled the force and doubled the mass, so I've already balanced out this equation. So my acceleration is going to remain the same as it originally was. So the acceleration on that second object is 2 meters per second squared because it remains constant with what that original object was as well. Really, on this slide, all I want to talk about is briefly talk about Newton's second law. Okay, so I don't know why I wrote that second first, but Newton's second law is what we're going to look at. So pretend that's actually in there. But anyway, Newton's second law is truly just force equals mass times acceleration. The big thing that we do want to recall here is anytime we're working with this equation, we really want to be thinking of this as my net force equals my mass times my acceleration of the system, right? And so again, kind of like we saw in the first part, if I give you a box and I have multiple forces acting on it, the only way that we can figure out what the actual acceleration or force on the box will be is if we break this up into components, right? So here's my tension pulling off at an angle. I need to break that into components of horizontal and vertical components, and then that way I can add these up and find the resultant. We'll see a lot more of recapping on this in the second section of notes as well, but it is a process we'll see pop up from here and there, and we want to make sure we're comfortable in solving. Okay, so hopefully a very easy example here, right? 3 forces act on the object. In which direction does the object accelerate? Right, just looking at this, I know it's definitely going off to the left. So that tells me it's, well, all of these go off to the left except A and C just go straight up and down. And then force 1 and force 3 are not equal and opposite. So I know that the resultant from those two would end up going downward. So it's going to be off to the left and it's going to be downward. And looking at my option, the only one that makes any sense is D. I bet you guys probably breezed through that without needing me, so I won't waste any more of your time on it. So then here, a couple definitions that I do want to give us. You'll see statics referred to from time to time. There are actually courses in college, particularly if you go into engineering, that are literally courses that are just built upon statics. And so let's kind of recap what that means. So static equilibrium refers specifically to when an object is at rest. Okay, so when it's static equilibrium, it's talking about objects that are at rest. Now we know equilibrium in general means that the net force is 0, right? It means that there's no acceleration. But static equilibrium again means that the object is specifically at rest. Dynamic equilibrium, or dynamics, which you'll see referred to from time to time, dynamics are equilibrium with objects that are in motion. So again, this is with objects that are in motion. So in other words, if it's in equilibrium and we know that net force is 0, if the object is in motion and in equilibrium, what that tells us is these are objects that are moving with a constant velocity, right? So these would be objects moving in basically straight line paths at a constant velocity. So dynamics and statics, you should be familiar with those terms. You definitely don't need to memorize them, but you should know what they're referring to anytime that they come up in context. And then these two terms are also very important. Inertial frames of reference are frames of reference we're used to. So for instance, the Earth, we actually assume that the Earth is an inertial frame of reference. Now technically, the Earth is not an inertial frame of reference, right? So what an inertial frame of reference is it's a frame of reference in which the acceleration is 0. So the idea there again is if I'm just standing on the surface of the Earth and I'm observing motion, then as far as I'm concerned, the observer is not moving, right? So if I'm standing here watching a car go by, then as I observe the motion of the car, from my perspective, I don't appear to be moving, right? My acceleration appears to be 0. Now I said technically, the Earth is not an inertial frame of reference, because we know that in actuality, right, the Earth actually is orbiting around the Sun, and as it orbits around the Sun, it has to have an acceleration, right, that pulls it towards the center of its circular path or its elliptical path. But I have to have an acceleration, so strictly speaking, the Earth is not an inertial frame of reference because it is accelerating. However, we assume for our purposes that the Earth is an inertial frame of reference. So then the alternative to that, you'll sometimes see the term non-inertial frame of reference thrown around there, which obviously just means it's not inertial and therefore its acceleration is not zero. And then the other term is just if it's an accelerating frame of reference. The most common types of problems that we saw like these were those elevator problems where what happens if the elevator is accelerating upward? What does that do to my apparent weight? What does that do to the scale reading if I'm looking at a scale? And things of that nature. Okay, so we actually did see a few of these non-inertial frames of reference last year. Again, anytime we dealt with acceleration or the like. But we do want to make sure we're pretty clear on what that says. So if they tell me it's a non-inertial frame of reference, then I know that the object is actually accelerating. The frame of reference, I should say, is actually accelerating as well as possibly the object. So little details that are very important to pay attention. But then this last example, even though it's very blurry here, is pretty easy if you can read it right. An elevator suspended by a cable is moving upward and slowing to a stop. So if it's moving upward, I know its velocity is going upward. But if it's slowing down, if it's slowing to a stop, I know the acceleration is working against the velocity, and therefore the net force is going downward as well, right? So which of the following is possible? Well, the net force is not zero because it wouldn't be slowing down. It would be moving at a constant velocity because it would be dynamic equilibrium, right? So it's not option E. And then the rest of these options, option A, the tension is higher than the force of gravity, which would mean it would be accelerating upward. That doesn't make any sense. Option B, these two forces appear to be equal and opposite, which means B is basically the same option as E, so we know both of those are out. Option C seems to make sense, and option D, the only problem with option D is we have those two forces, which if you look at them together, look like they're probably either equal in length or possibly greater in length. So again, that would have either a net force of zero or possibly a net force going upward. So my best option here is option C, right? The force of gravity is higher than the tension because I know that my net force is going downward, so this force has to be more than the tension pulling upward.